You are looking at the epicenter of a structural catastrophe in its dormant state. To the untrained civilian eye, this is merely a flat-packed furniture delivery a weekend project purchased to hold paperback novels and decorative You believe it is a simple matter of inserting tab A into slot B. This is a fatal miscalculation. From a forensic engineering standpoint, what sits on your living room floor is a highly volatile, uncalibrated, kinetic bomb. You have been conditioned by society, and by cheerful, wordless instruction manuals featuring cartoon mascots, to view this assembly as a harmless domestic chore. It is not. It is a high-stakes civil engineering mega-project, and your current operational readiness is severely compromised. Every year, millions of these structures suffer catastrophic failure, shelves bowing under microscopic stress, joints fracturing in the dead of night, entire units collapsing due to lateral shear forces. Today, we are going to deconstruct the precise engineering failures that you'll commit, the exact mistakes that turn your domestic storage unit into a structural hazard. If you fail to understand this profile, you are not just building a bookshelf, you are constructing a monument to your own hubris. Let us begin the forensic evaluation. Chapter 1. The inventory bypass and the hubris of blind initiation. Before any mechanical intervention can commence, an operator must conduct a comprehensive topographical audit of the raw materials. The primary failure mode of the amateur builder is assuming the manufacturer has provided a flawless, mathematically perfect ecosystem of parts. Not. You are dealing with mass-produced, globally sourced hardware with a margin of error that can compromise the entire architectural matrix. The civilian builder is impatient. You tear open the cardboard sarcophagus, glance at the first page of the schematic, and immediately begin forcing wooden dowels into the nearest available orifices. This is the first critical flaw in standard civilian operating procedure. The blind initiation. You have bypassed the inventory phase. You believe that counting 72 identical wooden pegs is a waste of your operational timeline? You are operating under the delusion that you can simply find the pieces as you need them. By scattering the hardware across a high-pile carpet, you have introduced a catastrophic variable into the environment. The carpet acts as camouflage. When you inevitably reach step 14 and require the specialized 40mm load-bearing confirmation screw, it will be gone, swallowed by the synthetic fibers. You will substitute it with a 30mm screw, telling yourself it's close enough. It is not close enough. You have just compromised the tensile strength of the entire primary axis. To pivot from this catastrophic failure, we must initiate the forensic staging protocol. You must treat the living room floor as a sterile surgical theater. Every single component must be extracted, categorized, and mathematically verified against the master schematic before a single tool is lifted. You must quarantine the hardware in rigid high-visibility containment vessels. You are not sorting screws. You are establishing the foundational integrity of your supply chain. Only when the inventory is verified at 100% can the physical construction commence. Chapter those. The Camlock catastrophe and kinetic pulverization. With the supply chain verified, we enter the active construction phase. This is where the operation transitions from logistical planning to applied physics. The primary method of securing the perpendicular joints in modern flat-pack architecture is the Camlock and nut system. It is a brilliant, cost-effective piece of engineering designed to pull two pieces of medium-density fiberboard or MDF together with seamless precision. However, the user's interaction with this hardware is where 99% of operations suffer a catastrophic structural break. I am speaking, of course, about torque hubris. The civilian builder fundamentally misunderstands the material science of MDF. You are not working with solid oak. You are working with sawdust and industrial resin, compressed under heat. It has the structural integrity of a stale graham cracker. Yet, when you insert the Allen wrench into the camlock, you apply the kinetic force of a mechanic tightening the lug nuts on a commercial track. You twist until your muscles tremble. You believe that tighter equals stronger. This is the second critical flaw. The deployment of blunt force kinetic trauma to solve a delicate tension equation. By over-torquing the camlock, you are not securing the joint. You are actively pulverizing the internal structural matrix of the wood. You are stripping the grip. You are turning the precise, engineered cavity into a hollow cavern of loose dust. The joint may feel tight in the moment, but you have introduced a microscopic fracture that will inevitably fail under the sustained load of hardback literature. The pivot to a superior solution requires a complete psychological overhaul of your kinetic output. You must decommission the primal urge to dominate the hardware. You must execute a calibrated, tactile restraint protocol. The Allen wrench must be held with a two-finger grip, utilizing only the torque generated by the wrist, never the shoulder. You turn the camlock exactly 180 degrees. When you feel the initial threshold of resistance, you terminate the rotation. Immediately, you are not locking a vault door. You are engaging a delicate friction seal. You must respect the biological limits of the particle board. Chapter 3. The cardboard diaphragm and lateral shear collapse. Once the primary skeletal framework is assembled, the entity must be stabilized. This phase requires an advanced understanding of geometry, specifically the vulnerability of the rectangle. A rectangular frame, no matter how tightly secured at the corners, is highly susceptible to lateral shear force. If pushed from the side, it will fold into a parallelogram and collapse. To counteract this, the manufacturer provides a backing panel. The third critical flaw in civilian operations occurs here: aesthetic dismissal. You look at this flimsy, pathetic piece of cardboard. You look at the 50 microscopic nails provided to secure it. You tell yourself, this is just cosmetic. It's just to hide the wall behind the shelf. I don't need to use all these nails. You hammer in 4 nails at the corners and call the operation complete. Or worse, you leave the backing panel off entirely to allow access to a power outlet. This is not a cosmetic oversight. This is architectural treason. That flimsy piece of cardboard is not a visual backdrop. It is a structural diaphragm. It is the only component preventing the entire unit from succumbing to lateral shear collapse. By skipping the nails, you have built a house of cards and invited the wind inside. But the most insidious threat in the stabilization phase is the blind puncture. When you do attempt to secure the diaphragm, you hammer the nails with reckless, uncalibrated strikes. Because the target area is only 15 millimeters wide, a deviation of even 3 degrees in your hammer trajectory will cause the nail to breach the internal laminate. You have permanently scarred the visible interior of the structure. You have created a jagged puncture wound that will mock you every time you reach for a novel. The superior solution requires a rigid adherence to geometric alignment. You must utilize a measuring apparatus to ensure the frame is perfectly square before a single nail is driven. You must deploy all 50 nails, spacing them with mathematical symmetry along the entire perimeter to distribute the shear load evenly. And you must execute the hammer strikes with absolute 90-degree vertical precision, utilizing a guide block to prevent trajectory deviation. Only when the diaphragm is fully integrated can the structure be considered architecturally sound. You have verified the supply chain. You have calibrated your kinetic torque to protect the MDF matrix. You have perfectly integrated the structural diaphragm, securing the lateral shear resistance. You stand the bookshelf upright. You look at the silent, towering monolith of engineered wood, and you feel a fleeting sense of victory. You believe the construction is concluded. You prepare to load the cargo. You are wrong. The visible structure is standing. Yes, the aesthetic profile is complete, but the true enemy, the invisible, entrenched, and highly resilient adversary, is simply manifested in the form of the orphaned component. You look at the single wooden dowel. You look back at the shelf. Panic initiates. Where does it belong? Was it a spare part generously provided by the manufacturer? Or is it the critical load-bearing linchpin of the central shelf? If you walk away now, you are leaving a structural void directly beneath your heaviest, and the operation is not over. The most dangerous, psychologically taxing phase of this engineering nightmare is about to begin. To achieve total operational victory, you must execute a forensic teardown. The orphaned component is rarely a spare. Manufacturers of budget flat-pack furniture operate on razor-thin profit margins. They do not distribute excess wood out of the goodness of their hearts. The dowel belongs in the primary load-bearing axis. You cannot fix this by ignoring it. You must rely on a targeted, structural regression. First, you must suppress your emotional frustration. You must systematically dismantle the upper quadrant of the unit, reversing your precise torque applications. You must locate the empty gaping cavity in the central shelf at exact point, where the vertical load transfers to the horizontal plane. You must insert the dowel, re-engage the cam locks, and rebuild the quadrant. But this is only the internal correction. To finalize the operation, you must execute the seismic relocation protocol. You must move the fully assembled 70-pound unit across the high-friction carpet to its final destination. If you push it from the top, the leverage will snap the base. If you drag it from one side, the torsion will rip the cam locks from their socket. You must deploy the rigid body glide. You must grip the unit at its lowest possible center of gravity, applying simultaneous, equal force to both vertical pillars, sliding it across the floor as a single, unified architectural entity. Only now is the structure truly secure. The supply chain was respected, the kinetic trauma was avoided, the lateral shear was neutralized, and the relocation was executed flawlessly. You have not just built a bookshelf, you have executed a flawless, multi-tiered civil engine containment operation. You have reclaimed your domestic infrastructure, but the manufacturer is relentless. They are already designing a new, more complex television stand with glass doors and misaligned hinges. The cycle of construction warfare is eternal. Tell me, operator, down in the comments. What is your most catastrophic failure in the flatpack hot zone? Have you ever fallen victim to hubris? Or are you still blindly hammering nails through the pristine white laminate of your daily operations? Report your structural errors below, so that others may learn from your casualties. The investigation is over. Dismissed.